All right. Again, people need to be responding to on campus if they haven't. There's still a couple of people that haven't done that, but we're gonna get going. All right. So on your screen right now is basically what we covered last class. All right. And obviously, we did a couple of examples that may have been a little bit confusing, getting patterns for the nth term of a series. Um, but this is very basically what we did. We looked at what an infinite sequence is, what a finite sequence is, what that actually means. Uh, we've gotten terms for explicit sequences. So this is a direct example of what we did last time. That's a sequence that switches positive and negative between terms and then has a larger fraction on bottom. Okay, and then a recursively defined sequence. And a recursively defined sequence is just a sequence that's where each term is defined by one or more of the terms before it. Okay. And then last we looked at factorials. Okay. And a factorial is very basically just a number where if you have a number factorial, it's every number up until that number multiplied together. So for example, 5 factorial, that's 1 times 2 times 3 times 4 times 5. Okay. And I'm going to hit an example of that here in a second. It didn't seem like people had many questions on the IXLs, but I'm going to leave this up for a second. And if you do have questions, we can try and go over it. So if you do have questions over the last IXL or the last class, please ask them now so we can address them before we move on to this new stuff. All right. So since there are no questions over this stuff, um, I want to do one example of factorial and just talk a little bit more about it. All right. So if I have n plus 2 factorial over n plus 4 factorial, we can simplify that. And this is a question that is very similar to something that would show up on an ACT or even next year. All right. So n plus 2 factorial, we can rewrite that as every number up until n plus 2 multiplied together, including the one before it, which in this case would be n plus 1 and n plus 2. Okay, and then we can rewrite n plus 4 factorial, again, as every number up until it, including n plus 1, n plus 2, and so on. And then we can cancel out common factors, all right? Now, the top and the bottom have common factors 1 all the way up until n plus 2. So we can cancel all those out. And we're left with this, okay? And obviously, I would rather you guys FOIL that and simplify it, but for now, this works. It's multiplication, not addition, yeah. So factorial is every number multiplied together. Okay, and one thing I didn't mention in the last class, factorials follow order of operations. They're kind of like exponents. In that if we have 2n factorial, that factorial only applies to the n, okay? And if we have 2n in parentheses factorial, that factorial applies to both the 2 and the n. All right, just a little caveat. All right, I get that, but why is it 1 plus 2 plus 3? Okay, in the denominator and in the numerator, we have n plus 2 factorial and n plus 4 factorial. Okay, what that means is that we're multiplying every number up until n plus 2 together. So we multiply, oh, these should be, sorry, these should be multiplication signs. I don't know why I'm adding them. I hope that clears it up. That's my bad. If 1 cancels out, why is it not 0 from the numerator? Because when you cancel out things, when you cancel out common factors, you're left with just 1. You're not left with 0. You can't factor out 0. So really, in the numerator, we can multiply everything up here by 1, and it will still stay the same. That's why this 1 is left over. Okay, and we'll practice this more. At some point, I'm going to get a worksheet out to you guys that just goes over this. But for now, we just need to know how to simplify these and what they actually mean. Okay, so questions about factorials. Okay, so that's pretty much everything we did last class. All right, now we get to some new stuff. All right, again, I would like you to write this stuff down. The more you physically write something, the better it sticks in your head. And this initial thing is very, very important. Okay, so we're going to start talking about summation notation. And as you write this down, I'm going to kind of explain how important this actually is. It's very important for probability. What we normally do in probability and statistics is we're adding very, very small things together. Okay, and that's really ultimately what calculus is. Okay, calculus is adding very, very, very small things together a huge number of times in order to get integrals and derivatives. It's basically looking at infinitely small things and getting their sums. Okay, and this is like the very, very start of that. Okay, so the sum of the first n terms of a sequence, again, a sequence is that you have a pattern of numbers that can be numbered. When we add all the terms of a sequence together, we get a summation. Okay. And this sigma, that's what this giant Greek letter is called sigma notation. And it's kind of like just a function, right? It's kind of like sine or cosine or f of something. It tells you what operation to do. And what this is telling you to do is to add all of the terms of a sequence together. All right, and there's a couple of names for these letters. I'll give you a second to just kind of catch up. So I'm going to kind of break this down part by part, and then we'll do an example. All right. This I, that's called the index of summation. And basically all that means is it's telling you uh, what the variable actually means in the sequence, okay? So we're dealing with I. That's telling you what to replace this number with, okay? And this number is called the lower limit of summation. Or just the lower limit. And then this n is the upper limit. Okay, so what this entire thing says is it says to take the sum of the sequence A from I equals 1 all the way up to I equals n. Okay, so for this example, and I think the best way to understand what this actually is saying is to do kind of like a really quick example, a really simple example, all right, of what I have written here on the bottom. Okay, so what this is saying is we want to take the sum of the sequence 3 times I from I is equal to 1 all the way up to I is equal to 5. Okay, so this looks like 3 times 1 plus 3 times 2 all the way up until 3 plus 3 times 5. All right, so then if we do that, we'd get numbers. So 3 plus 6 plus 9 plus 12 plus 15. And we can add all those up together, and that'd be the answer to that sum. Okay, but that's really what that is saying. It's summing 3 times I from I is equal to 1 all the way up until I is equal to 5. Okay, so again, I'm going to pause for a second. Are there any questions over what I have written? Yes, sigma notation is always addition. Okay, now it's not always going to look like this. Sometimes it can be a little bit more complicated, but it always means you're summing something up. You're summing a sequence up. Okay, and there is notation for multiplying, and it's been a while since I've seen it, but I think it's just this. It's not quite pi, but it works the same way. That's what this. You don't need to know this at all, but what this is saying is you're multiplying things together from I is equal to 1 all the way up until I is equal to n. Okay, but you won't see that for a while. Okay. Just another example. So this is what this is saying is we want to take the sum of 1 plus k squared from k is equal to 3 until k is equal to 6. Can I equal 2 and you multiply 2 and 5? Yeah, that's exactly what you did. Okay. And again, this example might clear a little bit of it up. This lower limit or this index doesn't always have to be I. Okay, there are different variables for it. and it doesn't always have to start at 1. Okay, depending on what you're doing, depending on probabilities, depending on whatever calculus you're doing, it doesn't always have to start at 1 or 0. Sometimes it can start later, sometimes it can start sooner. All right. So again, this is saying we want to take the sum of 1 plus k squared from k is equal to 3 all the way up until k is equal to 6. So if we rewrite that, we get 1 plus 3 squared plus 1 plus 4 squared all the way up until 6. So then we could get all those numbers, sum them together, and then we'd get an answer. Now on your homework tonight, what you're going to be given is this in this highlighted box. Okay, you're going to be given a sequence or a sum of different terms, and you'd have to find this sigma notation. Okay, and we'll go over examples of that. But first, we need to be able to work forward. Will the lower notation always go up by 1 each step, or can it go up by a fraction or something bigger than 1? All right, that's a good question. Keep in mind that we're only working with sequences. All right, and a sequence is always going to be numbered 1 through whatever. So it'll always be 1, 2, 3, 4. There's always going to be a first term, a second term, a third term, a fourth term. So it'll never be bigger than 1. Like, we'll never start at k equals 3, jump to k equals 5, and then k equals 6. Because what this is saying, what this sigma notation is saying, is we're adding up the third term, the fourth term, the fifth term, and the sixth term. Okay, so again, I'm going to pause for a second. Are there any questions about what you see up there? Okay, and as every new function we have, our new function has different properties. Okay, and I'm going to give you a second to just write these down and I'll kind of explain it and why they work. But the important thing is that we understand what each of these says and are able to use it. Okay, so I'll give you a second to write. If you want to leave space in between each one, that way you can kind of prove it yourself. But I will go through and explain why each one works. So this first property, um, we are summing c from I is equal to 1 all the way up until I is equal to n. Okay. Now, because there is no variable in here, there's no I in there, all we're doing is summing c over and over again n times. So if we were to simplify this, if we were to see what this is actually saying, we would have c times just 1, right? Several different times. Okay, so if you ever sum a constant, it's just going to be equal to that constant times the number of times you sum it. In the second property, that's saying we want to sum a constant times some number in a sequence from I is equal to 1 all the way up until I is equal to n. Okay, so if we were to rewrite that just by what we know, that would be c times a1, c times the first term, plus c times the second term, plus c times the third term, all the way up until c times the nth term. So each term in the sequence has a constant being multiplied by it. Okay, so if we were to factor out that constant, we get c times the sum of all the terms. And then in this big set of parentheses, that's just the sum of ai. So we get c times the sum of ai. And again, you don't need to know like these proofs, but I feel like understanding why they work is helpful, right? And then on the third property, this is saying we want to sum ai plus bi, so we're summing two sequences together from their first term all the way till their nth term. So again, if we were to rewrite this, I'm going to do this in a different color. This would be a1 plus b1 plus a2 plus b2, and so on, all the way up until an plus bn. Now, because we're just adding all of these things, these parentheses really don't matter. And we can add in any order, right? So we can put all the a's together. And all the b's together. And then this sum, a1 to an, that's just the sum of ai from I is equal to 1 all the way up until n. And then this sum of b's is the same thing. And these properties, they seem very, very simple. Sometimes they can be a little bit trickier because we need to move some things around or scale different things different ways in order to make these properties look apparent. Okay, And we're not going to be working a whole lot with that just yet. But properties very, very similar to these show up in calculus all the time. Okay, so for example, properties of integrals. These are pretty much them, just with different notation. Okay, so you're going to be working with these for at least next year. If you go into any other math above that, which I hope you do, you're going to be using these properties a lot in a lot of different places. Okay, so are there any questions over anything on your screen? So then this kind of brings us to our definition of a series. All right, so if we have an infinite sequence, the sum of the first n terms of that sequence is called a finite series. Or, and a lot of people say the nth partial sum. And again, this is just putting into words what we already did. So the sum of a1 plus a2 plus a3, the sum of a sequence, can be rewritten in sigma notation. Okay, now there is something called an infinite series or an infinite sum. Okay, you'll hear me refer to them as sums all the time. They're the same thing. But an infinite series is just a sequence that continues, and we're summing up all of those things together. Okay, and we'll take a look at what that looks like here in a second. But again, we're taking all of the terms in an infinite sequence, in a continuous sequence, and we can convert that into sigma notation. Just our upper limit is now infinity instead of a defined number. Okay, so I'll give you a minute to kind of write this down. This isn't too different than what we've already done, but I still think it's important. Okay, and then we'll go over an example of what an infinite series is actually, what that actually looks like. All right, so I want to do one example of an infinite series or an infinite sum. So I have this top example. This is a finite series, and the bottom one is an infinite series. But in order to kind of understand the bottom one, we can do the top one first. All right. So this is saying to take the sum of 3 over 10 to some power from the first power all the way to the third. So if we do that, we have 3 over 10 to the first plus 3 over 10 to the second plus 3 over 10 to the third. Okay, and if we rewrite this as decimals, 3 over 10, that's 3/10, which is just 0.3. 3/10 squared, that's 3/100. So we have 3/100ths, which is 0.03. And then 3/10 to the third, that's 3/1000ths, which is 0.003. Okay, so if we sum these together, if we sum all those together, we get 0.333. And in our infinite series, this just continues. So we'd get 0.3 plus 0.03 plus 0.003, and so on. Which would converge to just 1/3. So some infinite sums, they converge to things, and some diverge. So if we were to take the sum of all the natural numbers, so 1 plus 2 plus 3 plus 4, we wouldn't get a definite answer because it just continues. But if we take the sum of a kind of a clever, a different looking series, kind of like what we have right here, we get something that converges to a specific number. Okay, so even if we sum an infinite number of things together, we can still get a single number, which at first doesn't seem intuitive, but that's where we're going to be going with probability. Okay, so where does this show up? And this is just a quick example, and then I'll do a couple of examples from your homework. We've actually already done this. We've already used this in a way, and that's with logistic growth, not logistic growth, logarithmic growth. All right, so when we have a value and it grows at a certain rate per quarter, per month, per year, all we're doing is adding a whole lot of small values together. And we'll eventually get this equation. Now, we didn't use sums in order to get that equation, but this is technically a sum. Okay, now, I want to go over a couple of examples just so you know what to expect, and then I'll let you guys get to work. So the first several problems is just asking, is the sequence infinite or finite, and then how many terms does it have? All right, so this sequence is by definition finite because this upper limit is not infinity. Okay, so this is a finite sequence. And then it asks how many terms. So we have to take everything from 1 to 63, which just means there's 63 terms. Questions about that example? A little bit later, it'll introduce stuff where your index doesn't just start at 1, but it starts at 0, or in this case, -1. All right. So again, this is still a finite sequence because our top limit isn't a number, right? And then it asks us to find how many terms are actually in the series. All right, so there are 71 from 1 to 71. And then there's the 0 term, and then there's the -1 term. So there's really 73 terms. So we have to be careful about where our terms actually start and where they end. And that's kind of like part of the question. All right, and then later, the question I'm getting this from is like 70, 75, right? Where you will be given a sequence and you have to find the actual how you would get the sigma notation. All right. So the first thing we need to do is just to find how many terms there are. So there's 1, 2, 3, 4. There's 5 terms. All right, and if it starts at n is equal to 1, our lower limit is n is equal to 1, and our upper limit is just 5. And then we need to kind of incorporate what we did last class, which is where we need to find a rule of the terms, right? So how do we get from -2 to 1, 1 to 4, 4 to 7, and so on? All right, and you will have options for this, so you can kind of check. Yeah, so it would be 3n minus 5, as Hudson says, right? Because if we plug in 1, we get 3 times 1, which is 3. 3 minus 5, that's -2. Our second term should be 1. So 3 times 2 is 6. 6 minus 5 is 1. How did you know that the lower limit was 1? It will tell you. It'll tell you in the directions. Okay, and this is very basically your homework. Obviously, it gets a little bit more challenging in terms of finding the rule. But in most of these, at least up until like the 90s, you'll have options. All right, so I'm going to leave this open for a minute or two. If you have any broader questions, you can ask here. Otherwise, in the next couple minutes, I will be in Teams. I'll start a meeting, and you guys can kind of work, and I can be there to help out. All right. Ideally, we get this done today. I mean, obviously, it's due Tuesday, but if you have homework, it shouldn't be very much. All right. So I'll leave a couple of minutes for general questions, and then I'll hop over to Teams, and I'll help you guys out there. Okay, since there are no questions, I'm going to close this. And then the next like 2 minutes, I'll be on Teams. I'll start a meeting and you can ask a little bit more specific questions there. All right, so I will see you there.